this, right? Yeah. Format, okay. Okay, thank you. Hi, I'm very happy to be here and present. This is a great chance for me, and really wanted to speak because I've known Peter for a long time, since '99. I met him in Mexico. I was still in academia, and since then we really stay in touch. And actually, I had privilege to work with him in 2 places, in industry and then at NYU. And he's been always my great advisor, my inspiration, my mentor, and my friend, and my colleague, of course. Yeah, so this is a great opportunity. The work I'm talking about, it is pretty old. It is from Morgan Stanley Times, when I was working on practical work, and it's related to one of his classical papers, which I mentioned now. But before that, there is this, see, it's not working. It's not working, so should I go there? Okay, right. Mm-hmm. Yes, so this is his charming email from more than 12 years ago. In the morning, he was very early bird. All of a sudden, he has this revelation, and he sent me email about new Greek was born, and this is the story I'm trying to tell everywhere because he told me that I should. So what you see the message itself. So he suggested to call the correlation Greek by my name. And this was because I really spent a lot of time on correlation analysis. I work in commodities quite a bit, and correlation is of a great importance to us. I was looking at correlation risk. We wrote a paper with Alexander Eideland, and that's how, so all was, and then now I publish one more paper, big paper on correlations. So that was Peter's very charming style, as usual, very attentive, very human. The only thing which we change a little bit later is that because it's correlation, right, from letter O. So Alex Eideland suggested to add H, so it becomes like Greek letter RHO. So instead of Roza, he put RHOZA. Let's see. So the history of this work, in 2010, Peter came back to Morgan Stanley, because he was actually before that, as a head of market modeling team. It existed at that time. And at the same group, at the same time, I transferred from Valuation group, where I was for 5 years, and Peter became my boss. So my role was, I was responsible for commodities modeling. And for next 5 years, 2010, 2015, I worked with essentially 2 bosses. One was Peter Carr, which was my immediate boss, and another kind of very close friend and colleague, Alexander Eideland. And I considered this time the best time of my life, because I was very, that had this huge privilege to work with the greatest of minds and the nicest human beings. Obviously it is true for any field, but especially it's true for commodities that if you look at modeling work, it's not only about valuation, it's always also about calculation of Greeks. And that is quite important. And especially in commodities, it becomes really challenging because we really have a lot of inputs to valuation. For example, if you look at the valuation of power plant, then easily for 5 years, you can have like 500 inputs and more. So efficient calculation of Greeks is really, really important. And I spent a lot of time on that. So independently, I came across the classical Peter's paper, Deriving Derivative of Derivative Securities. where Peter actually used, he always was after technical, elegant math, and here in that paper, he suggested to use operator calculus. In the other papers, I should say, on this subject, but I think that was one of the first. And using this operator calculus, and you show you how, very, very simple idea, very elegant, that using this notion, you can express all, first of all, you can look at derivative, like derivative of the value as themselves, as values of certain contoured contingent claims, and also that you can express all partial derivative in terms of spatial derivative. For example, you can express Vega, sensitivity to volatility, through gamma, like a thing like that in other Greeks. And so before the conference, I tried to make some research to look at the like very recent state of Greeks, like papers devoted to Greeks calculation. There are plenty, and this particular paper, I think it's not being appreciated enough, in my opinion, even though it does have about 70 citates. I think it actually maybe kind of not forgotten, by no means, but in fact, what is important that this idea about expressing spatial derivatives through all derivatives through spatial derivatives has a very important practical application, and that's actually how I came to this paper. It wasn't because it's just of necessity to look at operator calculus. It was very practical, very concrete question I was trying to solve, doing practical work. And that's my idea. So I would like to, this talk, I would like to stress the practical application of his research, not only sophisticated and elegant maths, not only. So, so the first thing, for example, it can be realized that you can use these results to improve Greek's calculation. First of all, number one, Peter did everything for one dimension, but he did mention at the end that it can be generalized and left it for further research. That it can be generalized for for multiple dimension, and that's what the first thing I did. Look at a multi-asset situation, because in commodities we never look at one asset; it's always at least couple or even more. This is number one. And number two, when you look, for example, Vega-gamma relationship, you can reverse it. You can express Vega through gamma, and and that actually leads to a better stability and convergence property, and I will illustrate it on very simple examples. We had a lot of discussions. Actually, Peter was involved. We did common write-up. Peter suggested to include the exponential Levy models and stochastic volatility case. So I found this draft of write-up, and that's so I really decided this is about time I talk about this work. And by the way, this paper which I talked about, I'd like to mention also, officially it appeared in 2001. But I looked through research and I found some references in Paul Glasserman and Brody paper, and actually it was reference like a preprint with 1993, which means he wrote it being in Cornell, even not being in industry. So there was actually early of his research. So first of all, brief overview of Peter's work. So first of all, so this operator calculus, right? So if you look at standard problem, arbitrage-free claim with final payoff at expiration, we look at PDE, and it can be represented in operator form, right? Where L is, first of all, we have initial condition, the payoff, and we have this L, which is following linear operator. very standard and very well known. And what Peter said, that operator calculus treats one as just ODE, right? And L is like a constant. And what you do, you solve with formula, and then he shows it in the appendix that that's indeed the case, switching to log manis, etc. So pretty standard consideration, and expresses the solution in this term where this exponent can be represented through this series. And then actually things become really very transparent, because what you can do, you can differentiate this formal solution with respect to sigma, and immediately see that what you will have, because of the form, the operator actually sigma appears only in the first sigma square S square second derivative, and then easily you immediately see that the Vega, right, will be expressed as the expression essentially through the gamma with some multiplication sigma tau S square, right? And this is actually great because it is well known, for example, you can look at the Paul Glasserman book, that if you look at estimation of second derivatives, it's fundamentally much more difficult than estimating the first derivative, right? The convergence is much slower, and the stability as well. So there are certain rate of convergence. And in a commodity case, which is multidimensional case, this will be extremely useful. So that's what I first did, and that's what we discussed with Peter. So we switched to claim, right? And this is path independent claim with final payoff, certain final payoff. And in this case, operator takes this form, right? So now you don't have one underline, you have several futures. And following the same logic, we can derive the following relationship between gammas, cross gammas, and Vegas, right? And sensitivity correlation, which in that write-up, Peter suggested to Kristen like RHOZAS. So then you will, first of all, the simplest relationship will be sensitivity to correlation, which can be expressed through corresponding cross gamma. And then you have a little bit more involved, but not too bad, equations for Vegas. And so very, very, very simple. So once I will spend time on this cross gamma mostly. So the idea is the same. So you have first order Greek, right, which is easier to calculate. And then you have second order Greek, which is harder to calculate. And obviously this is really useful when you calculate, in industry, in most cases, we use finite difference. This is robust, right? So even the thing is that it's much easier to do this what we call Greek machine than, implement analytic formula, because mistakes do happen. And if you do this machine where you go up and down and calculate Greeks, this is much more robust and clean, and there's little mistake. Not instability, yes, noise maybe, but mistakes like formula mistakes less. And if you look at cross gamma, it's calculation by finite differences involves 4 perturbations. So you go up, up, down, 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 up, down, right? So this is most expensive Greek. And from the other hand, if we use this relationship through sensitivity of correlation, you would need only 2 perturbations of correlations. And it will be more stable and converges much quicker. So in order to show that, it's clear, but let me show you that's indeed is the case. So if we look at a very simple case, spread option, right, where so even zero strike and do calculation by Monte Carlo, then we can estimate cross gamma by finite difference through 4 perturbations, or using this relationship, right? And you can see if we use different, so this is one case only, if we use different set of random numbers, then evaluation of cross gamma by finite difference, which would be much more, had much more variance, then calculation would be much thinner. So this is number one. In number two, we can do the experiment. We can increase number of simulations and see how it is converging, right? So in this red line, this is because everything is known. This is just analytical value. The black line, it's estimate of by finite difference, and it's it converges. It's first of all, it goes up and down quite a bit. And if you look at the blue line, this is much better, right? So it converges much faster. And so this is the, so spread options, of course, I can see many other number of people, commodity people here. So of course, it's very well known that spread options are very important for energy markets, and they have numerous applications. For example, if we look at power generation, we can reduce it to a strip of daily or maybe over some blocks, a sparse spread option with certain PO. We have capacity, heat rate, right? Startup cost, right? You pay money to start up your power plant, and then future prices of power and fuel. Right. So in reality, of course, the evaluation of power plant is much more complex and involves optimization subject to some constraint. For example, if you, first of all, if you start a plant, you have to pay. If you start, sometimes you have to run it for a certain time. You cannot shut down immediately, or if you shut down, you cannot start it immediately. So it depends, like Alexander Lan was saying, there is no one model for power plant because each power plant is very individual, right? And that's the beauty and the challenge working in commodity space. And actually I work in that unit industry, but here for purpose of this presentation, what I did, I look at, now it's path dependent, right? Because it depends what happens on the way. It's not path independent anymore. In formally speaking, we cannot really apply these results because Peter's result were for only path independent payoffs. But nonetheless, so I did a simple experiment and look at very simple, extremely naive model of a power plant. And it was very simple. So we look only 1 month. In reality, of course, it's several years. And we assume this 30 years, and we have power plant only for 1 month. And let evaluation starts in T years, like several years from now. And I did not do like off-peak, on-peak prices, just daily prices, right? In order to, it can be done, this evaluation through simple Monte Carlo, right? So you simulate, first of all, future prices, and based condition on the future prices, you go inside the months and simulate daily prices. And then based on scenario, each day you decide, should you start the plant, keep it running, shut it down, etc., etc. So very simple, very naive, but nonetheless path-dependent situation. And the inputs, normal inputs to this problem is future prices. Then what typically is done, you look at implied volatilities, monthly implied volatilities, but then you also look at cash volatility inside the months, which is typically high, and also monthly correlations and correlations inside the months, which I assume for simplicity being the same. If we decided to start the plant, we need to pay startup cost per unit of power generation in each plant. Each day we make this decision what we do, and at the end we have value, right? Average of all Monte Carlo. you can, again, approximate the value of this power plant as a basket of spread options. And you can calculate daily volatility for each day, right, on this 30 times 30 days period. This evaluation will be obviously conservative because in reality, we do not pay startup cost. If it's running, it's already running, so we don't have to pay again. And for spread option, we know it's path independent, so we can apply this a relationship between X example, cross gammas, and sensitivity to correlation. And now what the purpose of this experiment to see if relationship this still holds, we can do that even for path dependent payoffs, right? So, and that's what I did. So so again, we did this. We have Monte Carlo, right? And then we calculate cross gamma sensitivity to future prices, for example, power gas, right? In this case, using 10,000 simulations, and then we look relationship, and then we calculate cross gammas through this relationship, which we got based on this Peter's result. And the result actually, in this again, this is very simple, simple model, but that's what I saw actually in the industry as well. I did the same experiment and using historical database, and that's what I saw. He actually decided to replicate by some simple model, and even in path dependent case, we see that actually we have pretty good relationship between cross gamma calculated by finite difference and cross gamma calculated from Roza. And that's, of course, this is very helpful that you can approximate the value of the power plant as spread options. So this is this result. So this is commodity part, and that's what I think, I believe, because that was real, right, which was very helpful in real life. And now, just in the remaining about 4 minutes, I believe, I will talk about the CV model, and that is actually a contribution by Peter. So in CV model, we look at the following SDE, and then do the same evaluation of European claim with final payoff. Then we can see, and we use future, right, and use future value of option, and then PD becomes extremely simple. And we can write this differential operator as well here. And the solution can be again written formally as in this form. And in this case, we have relationship between Greeks, which will generalize the previous relationship from the Peter's paper. And this is sensitivity to this parameter, the scaling parameter in front of source of volatility, kind of some vol, not vol of vol, but some scaling parameter delta. So if we look, this is case, more general case, that's what Peter was suggesting. And then if we look at CV case, CV as such, then this operator becomes this, and that's actually was really favorite thing of Peter, find some scaling, some symmetries, right, some groups, and some nice relationship. So what you can notice that if we look at the option value for option value, classical vanilla option value, then if we scale price and strike by factor lambda, and then we scale appropriately time as well, we see that the value of the option is being multiplied by lambda by that factor as well. And then standard trick, classical, you differentiate, put lambda equals 1, and you get this first order PDE for the option price, which looks like this, which means that this gives you opportunity to if you're observing option prices across different strikes, then And across different maturities, you can estimate delta of option. So that was, and then I did not put it here because I wasn't sure how much time I will have. Also, you can generalize this relationship between Vega. Yeah, I know. I have my timer here, David. Yeah, I'm watching. You said you didn't know at what time. No. I'm fine. Actually, I plan to talk about 25 minutes because that's what I was being told. So I'm very diligently following the rules. So Peter also suggested to use, to generalize, to use his favorite subject, exponential Levy model, which I did not put, but I'm hoping to present a paper, and then I will have all these results clearly written and reworked. So essentially the idea is that like actually, the previous speaker mentioned, when you look exponential Levy models, instead of PD, you have PE, DE, right? Integral differential operator. But the diffusion part, the sigma, right? You can still deduct the relationship between Vega and cross gamma, which might be also kind of practical and useful. So, and then of course you can do the same things using stochastic volatility model, using mixing Monte Carlo, etc. So that's what we've done with Peter some time ago. That was my research. And again, my main message that actually I did use his operator calculus to get some practical result while I was in academia. So that's what I think, which is really, really great about his research. And thank you very much for your attention.
Thank you so much, Roza. Thank you so much, Roza. And I'll never think about the Greek letter rho in exactly the same way ever in the future.
Yes,
so, any questions for our speaker from the floor? Can we check the Q&A just to be sure?
This is audio. Oh, that's okay. You can ask questions later.
Does anyone have any questions?
So for the CV model, we have closed form formulas for option prices.
Yes, yeah.
Can they be also used to obtain the Greeks?
Yeah, you can. Yeah, you can check everything. It's true, right? But CV model, first of all, first was more general case, right? And then CV model you can derive. So essentially, the idea, like especially the last relationship, the idea you can get this ODE, right? And you can connect delta. Sensitive like theta, right? And sensitivity to strike. And if you look at option prices, you can figure out delta. So that's main idea.
We have time for one more.
Roza, one more question.
Yeah, sure.
Thank you for bringing some exciting notes from both Peter and Alex. The great connection, connecting back to the work we've done together. My question is with regards to, you've done the role in the valuation in academia and again, research in terms of the various cross-gamma Greeks. So as part of your practical work, when we tend to backtest the valuations.
This is my proof. See, this is real.
So cross-gamma metrics, how does the backtesting with the real valuations in your practice resulted or yielded to the outcomes? Are they do they help effectively for us to predict the market movements and the valuation impacts?
So, Vidya, what is the question?
My question. So when we take the cross gamma metrics or various Greeks and assess the valuations and backtest day-to-day P&L from the trades on the book, especially for spread options, in your practice, the tests around using cross gamma metrics, do they help predict the P&L effectively?
Yeah, well, the thing is that, so my main idea is that cross gamma, if you do it, perturbation is not stable. That's the problem, right? So day to day, you cannot really rely on that. If you do through sensitivity using RHOZA, then it would be much more stable. And yes, the graph I showed you, actually, I did test on real data from, valuation of Monte Carlo dispatch model, etc., and I saw the same. So it's true. So it should be helpful. Now I don't recall. Well, I try to, like I have other colleagues from Morgan Stanley. The changes industry are a little bit difficult sometimes because it takes a lot of IT work, etc. So it's not, it's great theoretical result, but implemented, it's a different story, right? I did try to give that idea, and yes. So thank you for confirming this, Vidya. Appreciate it.
Well, thank you once again, especially for the commodities comments. Love that especially. Thank you. Our next speaker is down.